this presentation, we will begin our discussion about correlational studies, which investigate how certain variables are associated. We will learn how to use and interpret scatter plots, how to compute and interpret correlation coefficients, and we will discuss the assumptions that are made when such coefficients are used. Many research projects are what we call correlational studies because they investigate the relationships that may exist between variables. Before investigating the relationship between two quantitative variables, it is always very helpful to create a graphical representation that includes both of these variables. Such a graphical representation is called a scatter plot. Let's say that we would like to investigate the relationship between students' achievement motivation and their GPA. The table on the left includes a small group of individuals for whom we recorded the GPA and their score on a motivation scale. GPAs can range from 0 to 4, whereas motivation scores for this particular scale may range from 0 to 100. Individuals in this table were ordered based on their GPA, starting with the students with the lowest GPA, which is 2.0, and ending with the student with the highest GPA, which is 4.0. Just by looking at the data set, we can see here that, in general, as the GPA increases, motivation scores also increase. However, with a real data set, which may have hundreds or even thousands of individuals, we cannot detect a pattern simply by looking at the numbers. Therefore, a very useful strategy is to represent graphically the two variables to illustrate the relationship between them. Such a graphical representation is called a scatter plot. The graph on the right is a scatter plot for the two variables in our dataset, GPA and motivation. For every individual in our dataset, GPA values are represented on the horizontal axis, and motivation scores are represented on the vertical axis. So each dot on the scatter plot represents an individual from the dataset. Their location on the graph depends both on their GPA and motivation. Individuals with higher GPAs are located towards the right margin, and individuals with higher motivation scores are located towards the upper margin of the graph. For instance, Sam has the lowest motivation score and has the lowest GPA. There are two other students with the same GPA, like Joe, but Joe has a higher motivation score, so the symbol for Joe is located a little higher up. Tammy has both the highest GPA and the highest motivation score, so the dot that represents Tammy is located in the upper right corner. Scatterplots are not meant to be used in so much detail, though. When we have hundreds of individuals in a dataset, the scatter plot has hundreds of points. We cannot identify each point. The purpose of a scatter plot is to provide a general illustration of how the two variables relate to one another, to help us determine whether or not there is a pattern. In our example, we can see that, in general, as the GPA increases, motivation scores also increase. One of the students that doesn't seem to follow the general pattern, though, is Mary. She is one of the students with the lowest GPA, but has the maximum score on the motivation scale, so she's an exception or an outlier. Just like with any other types of graphs, when interpreting scatter plots, we must try to identify general patterns, as well as the outliers that do not fall into that pattern. Patterns can be described in terms of direction, the form of the cluster of points, as well as the strength of the relationship between the two variables. Let's first talk about the direction of the relationship that we're investigating. We say that two variables have a positive association or a positive relationship when higher values of one variable are associated with higher values on the other variable. One example of such a relationship is the relationship between the student's achievement motivation and their GPA. As we can see in the example on the left, when students' motivation increases, their GPA also increases. The arrow indicates the direction of this trend, or the direction of the motivation variable as the GPA increases. In contrast, we say that two variables have a negative association or a negative relationship when they go into opposite directions. For instance, the relationship between students' GPA and their number of unexcused absences. In general, students with lower GPAs have higher numbers of unexcused absences, and as the GPA increases, the number of unexcused absences decreases. This example is illustrated by the scatter plot on the right side, where the arrow indicates the direction of the absences variable as the GPA increases. The form or the shape of a scatter plot is also very important in describing the relationship between two variables. The example on the left illustrates a linear relationship. This means that the scatter plot describes a straight line. The plot describes a line because the y variable, which in this case is motivation, increases by approximately the same rate when the x variable changes by 1 unit. However, sometimes a scatter plot describes a curve rather than a straight line. This is because the rate by which the y variable increases is not the same, and it may even start decreasing after a certain point. The example on the right describes a curvilinear relationship between the variable age and the variable working memory. We can see here that working memory is increasing throughout childhood and adolescence, becomes relatively stable during adulthood, and then gradually decreases after the age of 50. Now, this is just an example based on simulated data, so you shouldn't start worrying about working memory right now. Scatter plots can also provide information about the strength of the relationship between the two variables. When the relationship is strong, the slope has approximately 45 degrees. As the relationship loses its strength, the slope approaches either the y or the x-axis. When we are investigating the relationship between two variables, the strength of the relationship is a crucial piece of information. Relying simply on the interpretation of scatter plots is too subjective. We need more precise evidence, and this evidence is obtained by computing a coefficient that measures the strength of the relationship we are investigating. Correlation coefficients measure the strength of the relationship between two variables. The formula presented here is for the Pearson correlation coefficient. For each individual, we compute the difference between the x and the y variables and their mean. These differences are then divided by the standard deviation of each variable and then multiplied. The results obtained from every individual are then added up and divided by the degrees of freedom, which is n-1. You're not going to have to do any of these calculations by hand unless you really want to, but statistical software computes correlation coefficients for us. It is important, however, to remember that correlations are based on the means and standard deviations of the two variables. It is also important to know that the Pearson correlation coefficient must be used only with quantitative variables and is based on the assumption that the relationship between them is linear. The notation that we typically use for the Pearson correlation coefficient is a lowercase r. Correlation coefficients can range from -1 to +1. When this coefficient takes the value 0 or values close to 0, there is no relationship between the two variables. When the coefficient's value is larger than 0 or positive values, the relationship between the two variables is positive, whereas negative values indicate a negative relationship. The closer the values get to 1 or to -1, the stronger the relationship between the two variables. When interpreting correlation coefficients, we have to make the distinction between strong, moderate, and weak relationships. Typically, regardless of design, values that are lower than 0.3 show that there is no relationship or a very weak relationship between the two variables. Values between 0.3 and 0.5 show a weak relationship. Values between 0.5 and 0.7 indicate a moderate relationship, and values larger than 0.7 show a strong relationship. These are just rules of thumb, they're not set in stone. The interpretation of correlation coefficients may depend on other factors, such as sample size, the area of research, and so on. Based on the criteria that we are typically using to describe correlations and the correlation coefficient of 0.62 that we obtained in this case, we can say, for our example, that there is a positive linear relationship of moderate strength between students' achievement motivation and their GPAs. These scatter plots illustrate what the relationships look like at different degrees of strength, so for different values of R. And we can see here both positive and negative relationships. We can see, for instance, that for a correlation coefficient of 0, the points have no direction, the shape is almost round, and we cannot fit a line on the graph. As the correlation coefficient increases, the observations group closer together and begin to describe a line. This line is hard to detect when the relationship is weak, like minus 0.3 for instance, but becomes more and more clear as relationships become stronger. When we compute correlation coefficients, we can also obtain a probability coefficient. We usually call this probability the p-value, and it shows the probability that the relationship between the two variables is equal to 0. Therefore, when the relationship between the two variables is strong, this probability is very small. The higher the correlation, the lower the probability. Correlations are typically considered statistically significant if the p-value is lower than 0.05. The researcher has the liberty to decide what a reasonable cutoff is, but this is the value that is typically used in social sciences. We call this value the alpha level, and we must report our alpha level when we report our results. In other fields like medical sciences, for instance, estimations must be much more precise. There is less room for error, so the alpha level may be smaller, like 0.03. We will explain p-values in more detail in the future, but what is important to remember right now is that each correlation coefficient comes with a p-value, and that p-value must be lower than 0.05 for the relationship to be statistically significant. SPSS computes p-values for us and uses the notation sig because it indicates the significance level. For the correlation coefficient in our example, the p-value was 0.03. Because 0.03 is lower than 0.05, which is our alpha level, we can say that this relationship is statistically significant. Notice that when we describe a relationship, we must always report 4 things: the strength of the relationship, which is given by the correlation coefficient, the direction of the relationship, which can be positive or negative based on the sign of the correlation coefficient, the shape of the relationship, which for Pearson correlations must always be linear, and whether or not the relationship is statistically significant. When using and interpreting correlations, it is very important to make sure that we know a few facts about the statistical procedure. First of all, in correlation, the order of the two variables is not relevant. The correlation between motivation and GPA is the same as the correlation between GPA and motivation. The order is not important when we formulate the research question or when we conduct a statistical analysis. Furthermore, correlation coefficients are only showing that the two variables are associated, and not that one variable explains or produces a change in the other variable in any way. For instance, we may find a high correlation between GPA and motivation, but this is not enough evidence to say that higher motivation leads to higher GPAs, or that higher GPAs increase students' achievement motivation. There are other statistical analyses that are used to try to provide evidence of causality. Only a correlation is not sufficient, even if such a relationship would make sense. All we can say is that higher GPAs are associated with higher achievement motivation. Regardless of how the two variables are measured, the correlation coefficient always has values between -1 and +1 and is therefore measured the same way. As we mentioned before, positive values indicate positive relationships and negative values indicate negative relationships. The Pearson correlation coefficient is based on certain assumptions, and we have to make sure that we meet these assumptions when we're using this coefficient. First of all, both variables must be quantitative. There are other types of coefficients that can be used with ordinal variables, but the Pearson coefficient can only be used with quantitative variables. Furthermore, it is also assumed that the relationship between the two variables is linear. Because the correlation coefficient is based on means and standard deviations, it is not robust to outliers. It is strongly affected by extreme observations. We call these individuals influential observations because they have a strong impact on the correlation coefficient. For instance, in our example, we can see that the correlation coefficient is 0.62 when the outlier is included in the analysis. However, when the outlier is removed, the correlation coefficient increases to 0.89. This one case, when included in the analysis, reduces a strong relationship to only a moderate relationship. In our example, this case makes such a big difference because we only have few individuals in the dataset. As a general rule, as the size of the dataset increases, the influence of extreme observations decreases. When describing the relationship between two variables, correlations are just one piece of the puzzle. This information is necessary, but definitely not sufficient. Other analysis should be conducted to provide more information.